Hi, I'm Jan Ozer. I'm here today with Chri Besenbruch, CEO of DeepRender, the developer of the DeepRender AI codec. We're here to discuss what AI codecs are, what advantages they deliver, and when we can expect to see them in deployment. Thanks for joining me, Chri.
Hey, thanks, Jan. Thanks for having me. Exciting to share the latest about AI codecs.
Cool. Well, let's jump into the presentation you have for us.
Yeah, I think it's best if we first start this presentation by defining what an end-to-end AI codec are. I mean, I come from DeepRender. I'm the CEO and co-founder of the company. And what I noticed is that there's a lot of confusion when we talk about AI codecs. So there are the traditional codecs, let's say AV1, VVC, HEVC. And then there's a lot of effort to make the traditional codecs better with AI. Super resolution, AI pre- and post-processing, or visual quality enhancement with AI. And none of this is related to an end-to-end AI codec. An end-to-end AI codec is shifting everything to neural networks. Or to be more precise, it's a paradigm shift. So in traditional codecs, we have an input video and we have this very familiar macro blocking and frequency transform to encode data to get the compressed bit stream. And with an end-to-end AI codec, we shift all of this towards a neural network. You can think of our entire encoding pipeline as one lightweight and complicated neural network that then takes the input video, input frame, and produces the bit stream. And then if we think about the decoding, it's exactly the same. We see in the old paradigm, macro blocking DCT transform, and in the end-to-end AI codec, we're sending the bit stream through another neural network to get the output frame. So all of it is shifted to an end-to-end AI pipeline, learns from data, and does not utilize or is compatible with any of the traditional codecs building blocks.
What are the advantages that this new architecture allows you to deliver?
Yeah, very good question, because whenever we do a huge shift in what's available, we need to justify it. Why are we even doing that? What's the benefit? And I first want to share some theoretical points, why DeepRender and I believe it's the future of video codecs. And then I want to share where we are today to give credibility to these points. But yeah, it might be a big overview on this slide, but the traditional codecs, they come with a lot of disadvantages. I mean, the standard bodies, Alliance for Open Media, has a slow development time because they require specialized hardware for efficient decoding, which then leads to fragmentation issues and licensing issues. I mean, Jan, you have covered very well on your blog posts the patent pools that even claim royalties on AV1 and VP9 nowadays. Then we see increasing computational costs, which is especially bad for encoding. And we see just no innovation in the paradigm. Like, it has stayed this way for at least 25 years since AVC and even earlier. And if we contrast that with AI and software-enabled codec, we have an increased innovation velocity just because it's new tech. Every new tech has a lot of ideas that are ready to be tested and implemented. AI codecs run on NPUs, AI accelerators. For some background, you might be familiar with Apple Neural Engine, or the new Galaxy phones with Galaxy AI, or the AI PC. And all of this has a specialized hardware component, the NPU, Neural Processing Unit, which is there to accelerate AI tasks. And AI codecs can basically piggyback off this hardware. We utilize it and don't need any specialized hardware whatsoever for encoding or decoding. And so with this commoditized NPU hardware, we resolve fragmentation issues in the user system. We resolve licensing and IP issues because it's a new start. There are no patent pools, there are no patent clashes, there are no overlapping ideas. AI codecs are symmetric. And so encoding and decoding has the same complexity or similar complexity. And so we don't have the 10 or 100x encoding complexity compared to decoding. And because it's a neural network codec, they're very flexible models, which allows us to fine-tune to your content and also innovate very fast. So all of these are just benefits, and it's a much better future and much better world if we manage to adopt and widespread adopt AI codecs in general.
Yeah, I mean, the hardware side has always been just nasty when it comes to actually deploying some of the technologies out there, and still are. As long as we're on that subject, why don't you walk us through where you see NPUs going over the next 5 to 10 years? Because currently, I think they're very well established in mobile devices, but they're not in smart TVs. It's mixed on the computer side. So, tell us where you see that market going, because decode is, at least for general purpose deployments, decode is going to be the big thing.
Oh yeah, for sure. And you're absolutely right. On the TV side, it's the most challenging platform because TV upgrade cycles are 6 to 8 years, and they're typically lacking behind on the hardware front. So AI codecs probably come to the traditional broadcasting world very, very late. They will start with the streaming platform streaming to mobile phones. Let's say user-generated video on demand, Netflix, Meta, YouTube, then to consoles and laptops, and then only after this to the OTT market and to the broadcasting world. As mentioned earlier, AI codecs require and benefits tremendously from NPUs. And here's some research of how many devices in circulation have NPUs. Right now, it's around 2 billion. It's mostly driven by mobile and Apple. Apple started very early with the Apple neural engine. I think it was the iPhone 13 and the M1 MacBook. And then now Samsung and Qualcomm have very powerful NPUs. MediaTek has started to have very powerful NPUs, and even Intel is in this race with their newest laptop offerings. And so we see a very fast increase, a very linear increase. Whenever you change your mobile device or your laptop and upgrade, probably get a device with an NPU. And so we expect 2.2 billion more NPU devices by 2028. And by 2030, we expect that all new smartphones, laptops, and consoles, all of them have NPUs, including televisions, at least on the high end.
Okay, well, none of this makes sense unless the quality is there. Why don't you walk us through the quality side as compared to traditional codecs like AV1, HEVC, and VP9?
Let me first start with a general overview about AI codecs and then go over what we at Deep Render have done. And so in general, and that's another kind of huge benefit of AI codecs, is not only is the quality to date already better than what's out there in traditional codecs, including AV1, including AV2, and including VVC with the VV encoder. But we also see that the quality improves exponentially. It's based on having a new paradigm. It's based on better neural network training. And it's based that we don't have any hardware hurdles. To give you some insight in Deep Render, we're pushing out a new testing model every 3 months. And every 3 months, we see improvements. And in the last 3 years, and also projected for 2025, we have seen a 25% relative compression gain improvement compared to our previous codec. And we don't see that stopping anytime soon.
Yeah, everything's low-hanging fruit these days. I mean, you're a new technology with a lot of runway to go.
The ideas we have are unlimited, and we are right now mostly limited by the resources. So we predict this to continue for quite some time. And then where we are today, because this is a future projection where we see that going in general, all AI codecs, not just Deep Render. But where Deep Render is today is that we are 40 to 50% more efficient than AV1. And with that, I mean SVT AV1 under low delay setting. So here we see two rate distortion curves. One is for the AOM CTC version 2 class A2 dataset, which features mostly natural scenes. And then on the right is a diverse dataset where we bundled gaming content, MCL JCV clips, social media content from the recently released YouTube dataset, just to give an idea that we're not just good in natural content, but in all types of content. I mean, your audience knows all about codecs, so I don't think I have to explain too much. Being at the top left in this curve is better. All of this is done in 1080p 30. And you can see that Deep Render just shifts the landscape to a fundamentally new trade-off level.
So it's SVT AV1, and you said low delay. Do you know which preset was used for that?
It's preset 7.
Okay. What about HEVC? Presumably that was X.265. Which preset was that?
X.265, preset slow.
Slow. Okay. And VP9, not a lot of people are using that for comparison purposes, but do you remember what preset you used there?
Yeah, it was a VPX, the VP9 version, and I think we used CPU used 4.
Where were you 6 months ago in terms of comparative quality, and where do you expect to be in 6 months from now?
6 months ago, we were at around minus 20% BD rate compared to AV1. And so just in the last 6 months, our team worked really hard and pushed that curve by 20 percentage points to the left.
So, what about performance? What about playback? What about encoding time?
A lot of these AI codecs are very heavy and huge. So what does performance matter if we can run it with 0.01 frame on a NVIDIA GPU? It's not a good product. Here are some metrics about encoding and decoding times. And I wouldn't say we are there yet. So the deep render codec is not necessarily yet ready for an all-purpose use case. But if we look, for instance, at encoding, and we look at it running on an M4 MacBook, utilizing the neural processing unit of it, we can see we get around 22 FPS, 40 FPS, and 50 FPS encoding speed for 1080p, 720p, and 540p content. And in encoding, because AI codecs are symmetric, so encoding complexity is roughly similar to decoding complexity, we are actually faster than, for instance, SVT AV1 encoding, even under the low delay preset 7 settings. This is a good story for encoding. Gets more complicated at decoding. So at decoding on the M4 MacBook, we can also decode in real time, even hitting the 60 FPS mark on the modern hardware. So 69 on 1080p, and then above 100 FPS on the lower resolutions. And these are not just theoretical numbers. We have FFmpeg binaries for testing. And Jan, I think you also interviewed my co-founder, where he went much more into detail and showcased these runtime numbers.
What would this look like on an iPhone? Say an iPhone, 12 or 13 that's got NPUs, but it's, 2 or 3 generations old.
Interestingly, not too different. So we are getting around 50 FPS on 1080p on an iPhone. But having said that, it's not the full story, because we're not necessarily limited by the FPS. We're actually limited by the thermals and the battery consumption. So battery consumption is relatively good on an M4 because of the node shift, the M4 is super efficient. But let's say on an iPhone 13 or iPhone 14 with previous generation chips, it's not necessarily the decoding FPS that limits us, it's the impact on battery lifetime.
What is the impact on battery life as compared to, say, HEVC, which is going to be decoded in hardware?
AI codecs will not be able to match hardware battery times anytime soon. We're seeing above 20 hours of playback on an iPhone for this. We are right now with our models on 1080p content at 10 to 12 hours. So starting an iPhone with a battery, let's say iPhone 15, 100% battery, running decoding continuously with the screen on. We get 10 to 12 hours, depending on the exact content type we're decoding. And SVT AV1 or the David decoder gets around 22 hours. And hardware decoding gets around 24 and a half hours.
Okay.
So there's still some work to be done, but for the state of the codec, I would say these are very, very strong initial numbers.
There's a lot of other AI codecs out there, or at least written about. How is your technology comparing to some of those? Because a lot of those just don't seem commercially viable given a lot of the encode or decode requirements.
This is a fantastic question because it's a topic I wanted to touch on anyways, which is the complexity and a big misconception about AI codecs. Most of the people we speak with from the industry, they agree that AI codecs are the future of the video codec industry, but they think about timelines 2030 plus, 2035 plus. And I think the main point for this is because in literature, in the academic literature, you very often see models which are good compression performance. They also outperform AV1, AV2, and VVC, but they have massive neural networks, 100 million parameters, a complexity of over 1,000 kilomax per pixel. And for comparison, as far as I'm aware, the AV2 specs say the limit is 16 kilomax per pixel. So they are nearly 100 times as complex as AV2. And so if you only see these literature results, and Microsoft is a company that has very good research in this field, but they approach it from the good compression performance, very huge model side, you get the feeling that AI codecs are not ready, or it will take at least another 10 years for them to get ready. That is a misconception, because there is some other, maybe lesser known research out there. One is Wave One, the company that Apple acquired, or Qualcomm, where Orca Wigger leads the AI codec team, who approach the problem differently. They start with very low complexity models that can reach real-time runtime. But their challenge is that then their compression efficiency is significantly worse than AV1. In the 8 model, they are 200 times worse than even X265. And so we have seen in literature this kind of this trade-off line between efficiency and compression performance. And what Deep Render has achieved, what our research team and engineering team has achieved, is that we have found the sweet spot. We're kind of in this point where we have low complexity and high compression efficiency, slightly better than the Microsoft models, so slightly better than DC, VC, VM. Very good model from Microsoft. But at the same time, we have more lightweight models than, for instance, Qualcomm, meaning we can actually run in real time and be fast. And then for anyone who's really interested in these numbers, here on the right is just a quick snapshot of BT rates, decoding complexity, and the parameters that are used for these different models.
Well, when do we see the first deployment of the Deep Render codec? What's your estimation of that?
In Q3 or Q4 2026, we'll see a major platform rolling out AI codecs, probably first for the Apple ecosystem. So it's still around 1.5 to 2 years off from right now, because there needs to be additional testing and there needs to be additional work in getting the power efficiency and the battery drain time lower. And that work will still take 1.5 years.
So it's interesting because the whole VVC decoder rollout really won't be well underway before then. And the industry is going to be faced with the decision to either go with NPUs, which are general purpose, or go with VVC, which is a single purpose integrated circuit. So I think the whole decode issue, the hardware side, is very favorable to the AI codec just because dedicated silicon for a decode is just not as viable, particularly as devices get smaller and battery life becomes more important. So
it's something Deep Render is betting on, because AI codecs surf on the trend of NPUs. They require them, and they are such a favorable headwind. When you spoke about the VVC hardware support, and to some degree still even AV1 hardware support, this is the entire pitch that I want to make to your audience. We can either continue the cycle of being hardware limited, taking decades or even longer to get codec benefits to end users, and hardware companies putting more and more silicon into codecs, or we just use what's already there, shift to AI codecs. And our future vision is to offer it as an alternative, not just to VVC, but as a replacement to AV1 and AV2. And yeah, we will see what the market decides.
And it's not like the market is betting on Deep Render. They're basically betting on AI. I mean, there's still going to be a race for the most efficient AI-based codec. It's just you have one platform that can play them all, as opposed to different platforms for VVC, HEVC, AV1, AV2, which obviously is slows everything down and wastes a lot of money.
Exactly. I mean, one of my favorite talking points is I would bet everything that AI codecs are the future. I cannot guarantee that's the Deep Render AI codec. I hope it is. I hope we're leading the field. But on the AI codec side, I can make that promise. I'm 100% sure that in 10 years, the vast majority of the world is decoding with any AI codec.
Yeah, I mean, it makes a lot of sense. Last question. We talked a few minutes ago before we started recording about the whole video coding for machines as compared to video coding for humans. Why do you see that as taking longer to develop for AI-based codecs than encoding for human beings?
It's a question of focus area, I would say, because AI codecs benefit a lot from being rolled out and adopted. It's kind of the first spark that ignites a fire. And for the first spark, widespread usage needs to be guaranteed, and therefore the support of the big platforms are necessary. I think after this is done, and humans are watching AI codecs, like in a very traditional sense in adoption, how the codec world works, afterwards, there are a lot of cool things that can build on top of AI codecs, including multi-codec worlds, codecs specialized for machines, or even working on compressed data, because it's some feature that AI codecs allow and make happen.
That's all I have. Chri, I appreciate you taking time today, and this has been very interesting.
Thanks, Jan, for having me. If you have any questions, follow-ups, or any of your audience, I'm available. I'm a bit advocator for the AI codec future, and I'm happy to support that in any way I can.
Very good. You take care.
Thank you. Bye.